Alright, in this video we're going to find an equation of a non-translated exponential function, and I've got a couple points that exponential function passes through. Before I start to address the points, let's take a look at what that means. An exponential function, generally speaking, is going to take this form where I have y equals some starting value times a base and it's raised to an exponent. And this little portion over here that talks about non-translated, all that means is not shifted left or right. If it were shifted left or right, we might see a little minus h or plus k if it's shifted up or down. But in this case, we've just got this relatively basic form of y equals a times b to the x. So we'll get rid of these and we'll go with that. So here's my form. I've got that form of an exponential. So my next step is then to take the information that I have and use that information to try to pinpoint exactly what A and B are. So I've got two variables there, two unknowns. And what that means is I've got to build two equations so that I can go through and solve a system of equations. So let's go ahead and plug these points in. When I plug these points in, I'm going to put in 250 for y, and that's equal to A times B to the second. And then when I plug my second point in, it's going to be 2 equals a times b to the fifth. So we've got a system of equations. Anytime you have a system of equations, you've got two options to solve. It's either substitution or elimination. Those are our two options here. So either one of these would work perfectly well. If I use substitution, I could just isolate A. That would probably be the easiest. Maybe we're going to use this one. So divide by b to the fifth, divide by b to the fifth, and then plug that value in for A up in the top, and then we can simplify from there. I'm going to use elimination just to show this process for this particular problem. All right, so in elimination, typically our goal is to eliminate or get rid of one of the variables so that we can solve for the other one. So this one's a little bit of a different case because usually in elimination we're going to add and subtract to the top from the bottom, the top equation to or from the bottom, and then one of them drops off, and then we have the ability to isolate the other one. In this case, though, if I add or subtract, it's not going to help because our right side, these are not like terms, and so when I go to try to combine those by adding or subtracting, it's not going to end up helping me out. So what we actually do in this particular case is we divide the top by the bottom, and I'll show you why that works here in a second. So we're going to divide 250 by 2, and that's going to give me a 125. And over here on the side, we'll show what this right side looks like. So the right side is AB squared, and then AB to the fifth. And so when I go to simplify this, I know that A divided by A, that just cancels. And that's exactly what we were after. We wanted to get rid of one of the variables. And in this case, by dividing, we got rid of the A variable. So I'm going to go ahead and further simplify this. If you remember from exponent rules, anytime I divide two expressions with exponents in them with the same base, I can combine those by subtracting the bottom from the top. So we're going to use that rule here, and then eventually we're going to end up with this b to the negative third. All right, so I've got b pretty close to isolated here. If you remember negative exponents, basically that just means the reciprocal, so we can flip this, 125, and that's equal to b to the positive third, and then I want to take a cube root. So when I take a cube root and I take a cube root, almost forgot to cube it there. There we go. Take my cube root of both sides. I get b all alone on the right side, and then on the left side, the cubed root of 1 over 25 is simply just 1/5. And again, just a reminder that we can cube root the top and cube root the bottom in order to get that. Okay, so I figured out my b value. I'm just going to take that and I'm going to plug it in up top. So wherever I see, let's plug it into this top one here. So let's take 250, or we'll get 250 is equal to A times 1/5 squared. This one in particular, 1/5 squared is 1/25. A. That's equal to 250. So last step, I'm just going to multiply both sides by 25, and a little quick math on the side of my head here. 6,250, that's equal to A. So I go to write my exponential function that's going to pass through these 2 points. I figured out my A value, or kind of my starting amount. That's the y-intercept in this particular case, is 6,250. And then my common ratio, if you think to geometric sequences, will be 1/5, also known as my base on my exponential function. So there's the equation for that one. So we want to look at another example here where we're given data in a table, and it's really the same, really a similar process. There is one shortcut when you have the data in a table, is that it's a little bit easier sometimes to identify a pattern. And so when I'm looking at, as long as I have these arithmetic x values, when I'm looking at the patterns in my y values, I'm looking for something to see if there's something that is consistently happening. And in this case, it looks like my starting value there, 3, is getting doubled to 6. And then I can take my 6 and double it and get the next term, and then double it and get the next term. And so what's repeatedly happening is 2. And this clues me into to tell me that this is an exponential function with a base of 2. This is a 2 to the x function. All right. So the only thing really left to do here is, I know it's going to be an exponential, and exponentials generally look like this. And so I've got to figure out that A value. Okay. We'll do the arithmetic, or sorry, the algebra here in order to set that up. So I've got this general kind of bare bones equation here. I've got to figure out what my A value is. I'm just going to plug in a point. So let me plug in 1, 6. I'll plug this point in here. So that's 6 equals A times 2 to the first. And if I divide by 2 and divide by 2, I end up with an A value of 3. I can just come back up and plug that up into my equation. But one thing I want you to recognize is that what I just came up with was the A value, but that's given by that point right there. That is that output. And so this always happens with non-translated exponential functions, in that if I can figure out what the A value is, that A value is the y-intercept. And vice versa. If I could look at my table and I know the y-intercept, I really actually don't have to do any of this work right here in order to find what my y-intercept is. I can just plop that y-intercept right in there for the A value and get a final equation that looks like y equals 3 times 2 to the x. So that's one way to do this, and that way is really just recognizing patterns and understanding that that A value is just a y-intercept. If we don't know that, and maybe we go through some processes of elimination and we recognize that it is an exponential, but I don't recognize what that pattern is, we can always build a system of equations as a fallback. And so let's go ahead and do that, go through that process. We're going to plug in the point 1, 6 and 2, 12. And we're going to build a system of exponentials by plugging these points in. So let's go ahead and start with our first point. That's 6 equals A times B raised to the first. And then over here, we're going to use our second point, and that's 12 equals A times B to the second power. So I've got my system of equations. Remember, we can always use substitution or elimination in order to solve systems. I'm going to show elimination. Substitution would be relatively easy and straightforward here as well. We could solve for either the A or the B in the top equation, and then plug it into the other one and simplify. Let's go ahead and go through the elimination because it's a little bit different. As we saw earlier in the video, give you one more example of that. So if I want something to cancel in this case, I've got to actually divide my top by my bottom. So I'm going to get 6 divided by 12 on the left. When I divide the right side, remember this actually looks like this, AB over AB squared. And my A's are going to drop off, and that's exactly what we're looking for in that case. So here, this is that rule of exponents where I'm going to subtract the bottom from the top. So I actually end up with b to the 1 minus 2, or just b to the negative 1. And in simplifying, again, a negative exponent means I take the reciprocal, so I'm going to flip this over and make it 2 over 1 is equal to b. I figured out my base. We already knew that should be the base based on our earlier work, but using the systems approach just confirms that we got that correct, b value of 2. So I now know b. I'm going to plug my b value into one of the equations. I'm going to get 6 equals a times 2, and then same thing here. I'm going to solve for a, and I end up with 3 equals a, and again arrive at that same exponential function equation.